So the equivalence relation tilde partitions the Cartesian product of the whole numbers with itself into mutually exclusive equivalence classes. The equivalence class, represented by the ordered pair AB, is the set of all ordered pairs CD in the Cartesian product of the whole numbers with itself, such that CD, the ordered pair CD, is equivalent to the ordered pair AB. That is, all ordered pairs CD, where A plus D is equal to B plus C. So as an example, the equivalence class for the ordered pair 0, 0, that is the set represented by the ordered pair 0, 0, 0, is the set of all ordered pairs CD such that 0 plus D is equal to 0 plus C. And so this is the set of all ordered pairs CD such that C is equal to D. And so we can call this or represent this as the set of all ordered pairs NN, where N is any natural number. Now, as we will see, the ordered pair AB corresponds to the number A plus the additive inverse of B. Now, if we have additive inverses for all our elements, then we can define subtraction. And so we can say that this is equivalent to A minus B. So note that if A plus D is equal to B plus C, then A minus B is the same as C minus D. Now the website scienceforall.org has a nice diagram illustrating the mutually exclusive equivalence classes. Notice for every ordered pair where the first component is greater than or equal to the second component or the second coordinate, those ordered pairs correspond to natural numbers. And in order to introduce negative numbers, we have ordered pairs where the first coordinate is less than the second coordinate. And so the set of integers which is denoted with an ornate or blackboard bold letter Z, is formally defined as the quotient set of the Cartesian product of the set of whole numbers with itself modulo equivalence relation tilde, that is, an integer is an equivalence relation, correction, is an equivalence class And the equivalence class with the representative, the ordered pair AB, is the set of all ordered pairs CD, where A plus D is equal to B plus C. And so addition in the integers is defined by the sum of the equivalence class of the ordered pair AB with the equivalence class of the ordered pair CD is the equivalence class of the ordered pair A plus C, B plus D. So we want to make sure that this definition makes sense and is not dependent upon our choice of the representative for the equivalence class. And so suppose that the equivalence class AB, the equivalence class for the ordered pair AB, is the same set as the equivalence class with the representative, the ordered pair A prime, B prime, and the equivalence class with representative, the ordered pair CD, is the same as the equivalence class with representative, the ordered pair C prime, D prime. Then we have that A plus B prime is equal to B plus A prime, and C plus D prime is equal to D plus C prime. Okay, we want to show that the sum of the equivalence class for the ordered pair AB plus the equivalence class for the ordered pair CD is the same as the sum for the ordered pair, the equivalence class of the ordered pair C prime D prime, correction, A prime B prime, plus the equivalence class of the ordered pair C prime D prime. So this is true when the equivalence class for the ordered pair A plus C, B plus D is equal to the equivalence class for the ordered pair A prime plus C prime, B prime plus D prime. So we need to show that the ordered pair A plus C, B plus D is equivalent to the ordered pair A prime plus C prime, B prime plus D prime. That is, we need to show that the sum of A plus C and B prime plus D prime is the same as the sum of B plus D plus the quantity A prime plus C prime. Now, since A plus B prime is the same as B plus A prime, and C plus D prime is the same as D plus C prime, we have that the sum of the quantity A plus B prime plus the quantity C plus D prime is equal to the quantity B plus A prime plus the quantity D plus C prime. Now, since these are all whole numbers, we can apply the associative and commutative properties to regroup them so that we have quantity A plus C plus the quantity B prime plus D prime is equal to the quantity B plus D plus the quantity A prime plus C prime, which was what was required. And so addition in the integers is well defined. That is, the result of the addition does not depend on which representative we choose for the equivalence classes. So next we will show that the set of integers, which again is the quotient set of the Cartesian product of the whole numbers with itself, modulo the equivalence relation tilde. This set is closed under addition. So proof. Let the equivalence class with representative the ordered pair AB and the equivalence class with representative the ordered pair CD be integers. Then the numbers A, B, C, and D are all whole numbers. And so the sum A plus C and the sum B plus D are also whole numbers. And thus the equivalence class of the ordered pair A plus C, B plus D is an integer. That is, the sum of the integer given by the equivalence class with representative the ordered pair AB plus the integer given by the equivalence class with representative the ordered pair CD is an integer. So next, we will show that addition in the set of integers is associative. So proof. Let the equivalence class with representative the ordered pair AB and the equivalence class with representative the ordered pair CD and the equivalence class with representative the ordered pair EF all be integers. Then the sum of the equivalence class of the ordered pair AB plus the quantity, the sum of the equivalence class of the ordered pair CD plus the equivalence class of the ordered pair EF is equal to the equivalence class of the ordered pair AB plus the equivalence class of the ordered pair C plus E, D plus F So this is the equivalence class of the ordered pair A plus the quantity C plus E, B plus the quantity D plus F, and since addition in the natural numbers is associative, this is the same as the equivalence class of the ordered pair, the quantity A plus C plus E, B plus D plus F. So this is the sum of the equivalence class of the ordered pair A plus C, B plus D, plus the equivalence class of the ordered pair EF, which is the quantity, the equivalence class of the ordered pair AB, plus the equivalence class of the ordered pair BD, plus the equivalence class of the ordered pair EF. And thus addition in the integers is associative. So next, we'll show that there exists the equivalence class of the ordered pair 0, 0 in the set of integers such that for any integer given by the equivalence class of the ordered pair AB, we have that the equivalence class of the ordered pair AB plus the equivalence class of the ordered pair 0, 0 is the same as the equivalence class of the ordered pair 0, 0 plus the equivalence class of the ordered pair AB, which is the equivalence class of the ordered pair AB. In other words, the equivalence class of the ordered pair 0, 0 is the additive identity in the set of integers. So proof. Since 0 is a natural number, actually 0 is a whole number rather, the ordered pair 0, 0 is in the Cartesian product of the natural numbers, whole numbers rather, with itself, set of whole numbers with itself. And so the equivalence class of the ordered pair 0, 0 is an integer. So let the equivalence class of the ordered pair AB be an integer. Then the sum of the equivalence class of the ordered pair AB with the equivalence class of the ordered pair 0, 0 is the equivalence class of the ordered pair A plus 0, B plus 0, and this is the equivalence class of the ordered pair AB. And the sum of the equivalence class of the ordered pair 0, 0 with the equivalence class of the ordered pair AB is the equivalence class of the ordered pair 0 plus A, 0 plus B, which is the equivalence class of the ordered pair AB. And so again, the equivalence class of the ordered pair 0, 0 is the additive identity in the group of, or rather in the set of integers.